Hello, my name is Roy Simpson. I'm an instructor of mathematics at Cosumnes River College in Sacramento, California. This lecture on intermediate algebra, we're going to focus on additional properties of lines. We've just finished a series of lectures on what a line is and what an equation of a line is, and that we did some, in addition to that, we also did some applications, which should be the focus of this in an intermediate algebra course. In this lecture, which is going to be split into two videos, we're going to talk about horizontal and vertical lines as well as parallel and perpendicular lines. The first part, we're just going to focus on horizontal and vertical lines, which is kind of a side topic in mathematics as well as parallel and perpendicular. But still, some of the results that you get from this lecture are usable in future courses. Let's go ahead and start this lecture with a table, creating a table of values to graph the equation y equals 0 times x plus 3. It might be tempting to ask, why am I even bothering writing 0x, because 0x is just 0. But it helps initially to see the pattern. So let's go ahead and build the table. It doesn't have to be a long table, but I'm sort of making it a little bit longer than it needs to be. And let's try some values for x, like a -2, a -1, 0, a 1, and a 2. When you plug -2 into that equation, you get y equals 0 times a -2 plus 3. And of course, 0 times -2 is just 0. So this gives me the output of 3. When I plug in a -1, the same thing happens here, that we get 0 times a number, which turns into 0 plus 3 is still 3. And in fact, you can continue down this list, you'll see it will always be 3. And we can, of course, use this information to quickly create a graph of this equation. Let's see, when x was a -2, y ended up being 1, 2, 3, so up here. When x was a -1, y was 3. When x was 0, y is 3. When x is 1, y is 3, and so on and so forth. And you see that when you do that, and in fact maybe I'll use a different color for this just because of the fact that it'll start looking like two x-axes. When you do this, you get a line that is actually horizontal. And this is essentially a justification for a theorem that we're going to say in a second. But before I do that, I want to mention that had we not written the 0x there, this equation would have looked like y equals 3. Every time you see an equation where it's a single variable like this to a first power, like y equals 3 or x equals 3, it's a very special kind of line. In this case, with y equals 3, it's telling me the heights, the y values, are always 3. No matter what value I plug in for x, y is always 3. Try x equals 7, y will still be 3 because there's no x that this depends upon. So let's go ahead and write this down in the theorem. The equation of a horizontal line has the form y equals k, where this k right here is just some constant, or, well, that's what we call it in mathy terms. It's a constant, in other words, a number. Could be pi, actually. It could be 3, it could be a half, it could be 1.7, it could be a -1.7. But no matter what, if it has the form y equals a solid number like that, then it's going to be a horizontal line. I'll take a really quick example here, just make one up. Example, let's go ahead and graph y equals a -1.218. A lot of people get intimidated by decimal numbers, especially when they go out so far, out to the thousandth. But this is not such an intimidating example. When you graph, make sure you label your x-axis and y-axis here. And note that this has that form, y equals a number. In other words, no matter what I choose for x, you don't have to make a table, but I'm just going to show you. No matter what you choose for x, your y value is always going to be -1.218. Right? So even choosing 2 points in a table, you can pretty much graph this quickly. It's 0, -1.218, and I don't even need x equals 1. I could try x equals 5, and the y value is still a -1.218. connect these dots, and we have a horizontal line. Great. So let's see what happens when we switch it up, when it's not y equals the number, but instead we look at something like x equals a number. And in fact, in this situation, this example right here, I'm just going to switch it up a little bit, and instead of having like x equals number straight away, let's try this. 2x plus 0y is equal to 4. Well, again, that 0y means that we don't have any of those y's. In other words, that's gone. But we'll still make a table here. Let me choose the right pen for this. In this case, I could choose values for x if I wanted to, but I'm going to illustrate this example or make it a more powerful example by choosing values for y. In other words, I'll make a little table like -1, 0, and +1 for my y values. You could always do this when you build a table for a linear equation. You could choose values for x or choose values for y, but often it's much easier to choose values for x because we're using the slope-intercept form or something like that. But in this case, it's actually pretty easy to substitute in for y as well. Well, when y is a -1, we have 2x plus 0 times a -1 is equal to 4. That just means 2x is equal to 4. Or in other words, x is equal to 2. Okay. And we find out that if we let y equals 0, the same thing happens. In fact, the pattern will continue, that no matter what we let y be, x will end up being a value of 2. Let's graph this situation. There's the x-axis, here's the y-axis labeled appropriately. And again, when x is 1, 2, y could be 0, it could be 1, it could be a -1. Well, right there I see what it's going to be. It's going to be a vertical line, right? You have 1, 2, 3 points, you draw a line through them, there's your vertical line. The equation of that line could have been written like 2x plus 0y is equal to 4, but it's much better actually to clean that up and just write it as 2x is equal to 4, or even much better than that is just write it as x equals 2. So that's the equation of this line. And note that previously we had a horizontal line that had the equation y equals, well, in this case right here, -1.218. So if you have y equals a number, it's horizontal. If you have x equals a number, it's vertical. Let's go ahead and write that down in a theorem. The equation of a vertical line has the form x equals a number. I wrote it as x equals k, but remember k is just a constant, or in other words, a number. There's by the way, a lot of names for constants in mathematics. We call them numbers, constants, or if you're more advanced in mathematics, we call them scalars. It's another name for them as well. So if you want to impress your math instructor, say, oh, I was adding this scalar to this other scalar. That's a very impressive way to refer to a number. Truly, there's only a couple properties concerning horizontal and vertical lines that I want to mention here. Most other properties about lines are pretty interesting. These are kind of trivial properties. I'm going to go back to our horizontal example. And if you look at this horizontal line, it could be any horizontal line really. Let's talk about the slope of this line. How do you calculate the slope of a line? It's rise over run, correct? It's just m is equal to change in y over change in x, delta y over delta x, or rise over run, or as I often say, change in output over change in input. In that language that I'm using, output and input, again, I'll just restate it, that language is being used because later on you're going to be introduced to an idea called a function, and if you continually talk inputs and outputs prior to talking about functions, it makes your life a little bit easier. But in this case, let's go ahead and calculate the slope of this line. I see that I labeled this point, now that I'm looking at it, I labeled this point That's because I'm pointing at the x-axis. Okay, so maybe I will erase that. There, that's why I should use a different color for axes and also a different color for the lines. Okay, this red line here is actually the horizontal line, and we have a couple points on that horizontal line that we already have indicated. So let's use those points to calculate the slope of this line. Some people probably already know what the slope is going to be if you consider that the slope of a line pretty much indicates the steepness of the line, and this line has no steepness at all, so we would expect something pretty trivial for the slope here. So I'll take the difference in the y values. Let's see, I'll take this as my first one I'm going to write down, so a negative 1.218 minus the second y value here, so another negative 1.218. Be careful because you're subtracting the negative. And then divide that by the difference in the x values, 5 minus 0. That numerator, negative 1.218 plus 1.218, so that becomes a 0. Denominator is just 5, but 0 over 5 is 0. And in fact, this is true for all horizontal lines, that their slopes will actually be 0. So let me write that down as a theorem here. The slope of a horizontal line is 0. It should make sense, right? Because it has no steepness to it. Now, if you think about the other kind of line we've talked about, vertical lines, those have a very steep slope. If you think about it, I mean, it's a cliff face, isn't it? That's so steep, there's no way you could climb that. It's impossible, in fact, to climb something like that. Well, unless you're Spider-Man or something like that, I suppose that's possible. So let's use this as our example for a vertical line here. I'm going to label these points. This was x equals 2, y equals positive 1. This is x equals 2, y equals a negative 1. And let's calculate the slope of this vertical line. We expect it to be something large at least. So let's see, difference in y values, so 1 minus a negative 1, over difference in corresponding x values, so 2 over 2, or 2 minus 2. So the numerator, 1 minus a negative 1, becomes a positive 2, actually. The denominator is 0, and now we have this dreaded division by 0. That division by 0, you cannot divide by 0. That leads to something called undefined, or a number being undefined. There's a lot of justifications. If somebody's just told you in the past that a number is undefined if you're dividing it by 0, I'll give you a justification for this at the end of this video. But for right now, it's good to know that the slope of a vertical line is considered to be undefined. I'll go ahead and write that as a theorem. And what I try to preach in a classroom environment is that you should try to understand mathematics rather than memorize mathematics. And this is a concept that can be somewhat understandable, especially the horizontal line having a slope of 0. That's very understandable. But I think students have a hard time understanding why the slope of a vertical line is considered to be undefined. So for all intents and purposes, we are actually done with our discussion on horizontal and vertical lines, but I'm going to have this little addendum here where I'm going to convince you as to the reason why we consider the slope of a vertical line to be undefined. Now remember the fraction we had before, this fraction we said is just undefined. The reason why we call that undefined is because, well, what if we started with not the number 0 on the denominator, but something close enough to it? Like, oh, I don't know, 1/100th. 1/100th is very, very close to 0. I mean, well, it depends on what you're talking about. 1/100th of a mile is not so close to 0, but 1/100th of a millimeter, very close to nothing, right? So it just depends on the units you're talking. But in this case, 1/100th is not 0, but close. And if you look at this number when I write it out, that means 2 divided by 1 over 100. Remember, I could change the division to multiplication. So that's 2 times 100 over 1, right? You change it to multiplication by flipping or taking the reciprocal of the second fraction there. And this number becomes 200. So in reality, 2 over that very small number is the same as 200. Well, this doesn't convince you of anything yet, but let's suppose that number on the denominator there was 1 million. 1/1 millionth, I'm sorry. 1/1 millionth, that's extremely close to zero. If you had 1/1 millionth of a dollar, you'd essentially have nothing, right? So this is almost like 2 over 0, very, very close to that. So let's see what this number actually is. 2 divided by 1 over a million. Well, that's the same thing as 2 times 1 million over 1, which is the same thing as 2 million. And this should be like an aha moment. That you see, the smaller I make that denominator, the closer I get that denominator to 0, the larger the actual number is. So if I had 2 over a ridiculously small number, then in reality that number is huge, incredibly huge. Okay? And as we get even closer to 0, it gets massively huge. So the idea is, when you think about the steepness of that vertical line that we had earlier, this one right here, that's a massively huge steepness, isn't it? I mean, that's so steep, it's hard to fathom how steep that is. How do you put a label on the steepness of that? And that is exactly what we're talking about as far as the size of 2 over 0. 2 over 0 ends up being, well, 2 over a number close to 0 ends up being ridiculously huge. And that's why we consider 2 over a very small number, like near to 0, to be undefined, because we really can't define it. I mean, it never stops growing. You can't just say, oh, it's like 2 billion. Somebody could trump that and say, well, it's 2 trillion, right? So we call it undefined.